carbon nanotubes, their synthesis properties and their applications. So before going to this talk, this is what the overlay of my today's class. We are going to give introduction to the carbon nanotube, and we are discussing synthesis properties and applications. So before going to discuss about the carbon nanotubes, we would like to discuss the research work which is going on carbon nanomaterials, particularly this, as we have discussed earlier, the carbon silicon, both elements will play a major role in electronics or in science and technology. So within carbon, if you see the publications or output of the research in the form of publications, if you see fullerenes, carbon nanotubes, graphene, the number of publications, fullerenes are having 15,000, around 14,651, and carbon nanotubes 92,000, graphene 1,19,034. This is what the output up to now, what our research people have reported. So we know well already the allotropes of carbon. This is a diamond, graphite and fullerene. In this lecture, we are going to discuss about carbon nanotubes. This is one of the allotrope of carbon. In this field, that is carbon nanomaterials field, 2 times people have been awarded by Nobel Prize. In 1996, in 2010, 2010 for graphene, and this is for 96 for fullerenes. The classification of carbon nanomaterials. So we are classifying the carbon nanomaterials in 3 types: 0-dimensional, 1-dimensional and 2-dimensional. Even 3-dimensional materials are there. For 0-dimensional nanomaterial, carbon nanomaterial, fullerene is the best example. Even our food item, that is an even you can, if you want to remember easily, see what it is. It is a bulk material. It is a name called bundi. Just you see, you can compare. So both are spherical in nature, but the bundi is a bulk material and our fullerene is a nanomaterial. See, in all the directions X, Y, Z, we are having in the size of these fullerene is in nano size, in nanometers. The bulk, it will be in millimeters, microns, or even centimeters or meters, whatever it may be. That is what the bulk material is. Even one more bulk material, that is 1-dimensional nanomaterial. Let us see. The best example is Kara. Just you may have seen in our, it is why I am taking these food items, or as an since we are seeing them in our daily life, so we can remember easily. That's what the fullerene is a 0-dimensional material. Now carbon nanotube is a 1-dimensional material. It will be look like a carbon nanotube. You see this, that is a Kara is having 1 dimension, it is in centimeters or this thing, but remaining things also it is in millimeters. Still it will be coming under bulk. But if you come to the carbon nanotube in 2 dimensions, either it may be in X or Y, it will be in nano, and in one direction it will be in microns or millimeters. That is the carbon nanotube. Carbon nanotube will come under 1-dimensional nanomaterial. Similarly, one more material, 2-dimensional nanomaterial. See that then one more sweet, that is this is a Mysore pak. Just you can compare. This is a 2-dimensional nano bulk material, X, Y, Z. Everything is in millimeter or centimeter, or even more than that also we can even we can make it. But if you come to the graphene, XY direction it will be in nano size. In one direction, Z direction, it will be in microns. The SEM and HR10 image of the graphene was shown in the present slide. You see the hexagons of carbon atoms in TEM image, that is a 2 nanometer scale, which was shown in the present slide. Just you see this is what the length of uh, the we are giving the scale here. This is 2 nanometers. See in 2 nanometers how many hexagons are there. You just clearly you can see the hexagons here. Carbon atom, 6 carbon atoms. It is forming hexagon, and at the corner dislocation of hexagons you can see, that means carbon atoms were displaced or they are not in order. And it is the TEM image of graphene. Graphene is a two-dimensional material. Zero-dimensional material polyurine, one-dimensional nanomaterial is carbon nanotube, and two-dimensional nanomaterial is graphene. So with this, I think we can remember well. Okay, 0, 1, and 2. It's a polyurine, carbon nanotube, and graphene. Okay, graphene. The carbon nanostructures is based on the stacking, based on the rolling, based on the warping. Even we are classifying as a zero-dimensional, one-dimensional, and two-dimensional. CNT, carbon nanotubes. So how we can define CNT? The carbon nanotubes are rolled graphene sheets, or otherwise the rolled graphene sheet is known as carbon nanotube. This is the simple definition of carbon nanotube. The rolled graphene sheet is known as carbon nanotube. The rolled graphene sheet is known as carbon nanotube. And we can compare this even with noodle. Just this, if you compare the physical and chemical properties of these both things, it is very different. This left side it is very soft and the density will be high. The right side it is very hot and hardness of these carbon nanotubes will be very high, and even tensile strength will be high. Even we can compare these carbon nanotubes with steel, not with even noodles or the one-dimensional bulk material. The rolled graphene sheet is known as carbon nanotube, and the STEM image of STM image of carbon nanotube and the hexagons can be seen clearly in the image. Just you see here, and this left side was simulated diagram. And graphene is a monolayer or single layer of graphite. Okay, if these a number of graphene layers are stacked, that is known as graphite. If you are taking only graphene as a monolayer, and if you are rolling it, we will get carbon nanotube. If it is not rolled, it is a graphene sheet. If it is warped in spherical form, that is a polyurine. This is the major difference between these three things: warping and rolling and stacking. If the stacked one, if you are collecting one, this is a graphene layer, that is known as graphene actually. Okay. If you are rolling it into one-dimensional tube, that is carbon nanotube. And if you are warping, it is a polyurine. Synthesis of carbon nanotubes. Carbon nanotubes can be synthesized in 3 ways. One is arc discharge method, second one is chemical vapor deposition method, and third one is laser ablation method. Let us discuss one by one. It is look like in our KH experiment, which we have discussed for polyurine synthesis. The similar manner, the CNT can be synthesized. That is arc discharge. In arc discharge method, what we do, just we are taking an micron size diameter graphite electrodes, okay, and we are keeping in vacuum chamber. The diameter of the electrodes was in microns, and these electrodes were doped by rare earth elements. Why we are doping these electrodes with rare earth elements? If you want to control the diameter of carbon nanotube we can. If you want to make only single wall carbon nanotube, we can make. If you want only multi-wall carbon nanotubes, we can make. Multi-wall means if two graphene layers are more than two or more than graphene layers are rolled in one-dimensional manner, that is known as multi-wall carbon nanotube. If single graphene layer is rolled in one-dimensionally, that is known as single wall carbon nanotube. The diameter of the single wall carbon nanotube will be less than 2 nanometer in one-dimensional, that is a single wall carbon nanotube. In multi-wall carbon nanotube, the diameter of these carbon nanotubes will be greater than 2 nanometers. Now we are keeping electrodes and we are supplying the DC power into the electrodes. What will happen? Normally at anode oxidation will take place. Due to oxidation, what will happen? The carbon atoms will vaporize from anode, and the vaporized carbon atoms will be precipitated at cathode. Those precipitation will be taking place in one-dimensional manner. If those carbon tubes are precipitated in one-dimensional manner, we get carbon nanotubes. If your electrodes are having these rare earth elements, niobium, tantalum, this type of things, what will happen? You will get single wall carbon nanotubes. If your electrodes does not have these rare earth elements, you will get multi-wall carbon nanotube. The conditions for these CNT synthesis is we are maintaining the temperature is around 3000 degrees centigrade and helium atmosphere, and the pressure 500 torrs. This is about arc discharge method. So let us go for another method, that is laser ablation method. Laser is a highly energetic ray. We know well already. If you are sending a laser ray on graphite, what will happen? The surface carbon atoms will be coming out from graphite, and those atoms will vaporized from graphite, and they vaporized carbon atoms will be precipitated on the substrate surface. Substrate was hanged and it was connected to heater, and we can rotate this substrate in either in clockwise or anti-clockwise. Once if you send the laser beam on graphite or target, so now our case target is graphite. If you send the laser beam on graphite surface, what will happen? Surface carbon atoms will be ejected from graphite layer, and those atoms will travel to the substrate surface, and they will be coated on the substrate in the form of tubes. This vaporized carbon atoms, we are naming it as flume. Okay, flume is nothing but it is like an smoke. Okay, the carbon atoms, a bunch of carbon atoms will be ejected if you are passing laser beam on graphite surface, and the entire process will be happening in vacuum chamber, and the plume will travel to the substrate surface. And why we are having heating provision to the substrate in the present laser ablation method chamber is normally the substrate will be at room temperature, and the generated flume will be at high temperature. This high temperature flume, if it is depositing on substrate at room temperature, suddenly this coating or deposition may not take place properly. That's what, in order to maintain the temperature or in order to balance the flume temperature, we are attaching our substrate to heater. If you attach this heater, what will happen? Substrate will be at high temperature, and high temperature flume will be deposited at high temperature itself. At the end, we get the deposited carbon nanotubes on the substrate surface, and we will collect them and we will purify them, and we will use it for different applications. This is the second method. First method is arc discharge method. Second method is laser ablation method. Let us see the third method, that is chemical vapor deposition method. The chemical vapor deposition method, this cylindrical tube you see here, that is made up of with quartz, because quartz can withstand high temperature. This is the quartz reactor. Okay, this quartz reactor was surrounded by heating coil. Either heating coil may be it is having a energy source, it may be a heat energy, or it may be a plasma, or it may be a some other, it is a microwave or any other form. Okay, this heating coil will be heated if you are supplying electrical energy or any other energy. So now heating coil, if it is since it was surrounded, our quartz tube was surrounded by this heating coil, and quartz tube will be heated. And this is what the heating provision what we are having in our CVD, chemical vapor deposition method. At present in CVD we are having 3 zones. So let us keep one substrate in any one zone. Let us take a zone 1 and let us keep substrate. We are keeping zeolite. Zeolite is a mesoporous material, and in that zeolite, so we are going to grow our carbon nanotube. Zeolite is a mesoporous material. The pore size will be in between. It is a meso pore means 2 nanometer to 50 nanometers. The pore diameter will be 2 nanometers to 50 nanometers. In this zeolite pores, now we will grow the carbon nanotubes. This is the left side. We are having a gas purging mechanism, that is hydrogen, argon, and methane. If you are purging these 3 gases at 900 degrees centigrade or 1000 degrees centigrade, what will happen? Argon is an inert gas, and hydrogen is in like a small amount of hydrogen only we will send. It is like an catalyst. The hydrogen and methane at high temperature, what will happen? They will burn, and they will due to the combustion of this methane, what will happen? Methane or ethane or propane. So we have to take one carbon source to grow carbon nanotube. If you are sending this gas from left side, what happens? The methane will decompose, and the entire quartz reactor will be saturated by carbon atoms and hydrogen atoms. Okay. Now these carbon atoms will precipitate in on the surface or in on the pores of zeolite. Zeolite, since zeolite is having a pores, however the pores are there, and so whatever shape the zeolite is having, according to that shape, the carbon nanotubes precipitated. So if the length of the carbon nanotube can be controlled, or the diameter of the carbon nanotube cannot be controlled in this method, because we are using an mesoporous material. The pore diameter is varying from 2 nanometer to 50 nanometers. We cannot control we can control the precipitation, but we cannot control the atom precipitation in specific manner. We cannot control the precipitation of atoms. We can control the environment, but in one dimensional we can control either if you want to get millimeter or micron length carbon nanotubes, we can get, but the diameter of the carbon nanotubes cannot be controlled by this method. And at the end, what we will collect the zeolite, and we will wash it with hydrofluoric acid, and zeolite will be dissolved in hydrofluoric acid, and we will collect the carbon nanotube. This is a third method, that is chemical vapor deposition method. What we have done in this method, we have taken quartz tube, and we have heated the quartz tube up to 900 degrees centigrade or 1000 degrees centigrade, and we have sent methane gas, and methane gas will be decomposed, and decomposed methane gas will give carbon atoms, and the entire reactor will be saturated by carbon atoms. Once the reactor is saturated with carbon atoms, what will happen? The precipitation of carbon atoms will take place. That precipitation will take place in the pores of zeolite, and once the carbon nanotubes are grown in zeolite framework, we stop the experiment and we will collect the geolite and we will dissolve the geolite in HF, and HF will dissolve the geolite framework and we get carbon nanotube. Carbon nanotubes are insoluble in HF. Geolite is soluble in HF. We can collect the carbon nanotubes at the end and we can functionalize the carbon nanotubes and we can use it for these various applications. This is the third method to synthesize for the synthesis of carbon nanotubes. These are the parameters for chemical vapor deposition. Quantity we are using geolite, temperature 1000 to 1100 degrees centigrade, methane gas, alternate carbon sources we can use, camphor, ethane, propane, any other, even ferrocene we can use, and time duration maybe half an hour to 1 hour. So we can get from 0.3 to 3 grams of carbon nanotube. Based on the diameter of the carbon nanotube, we can classify the carbon nanotubes into two types. One is single wall carbon nanotube and multi-wall carbon nanotubes. Graphing, rolling will be happens in three ways. So based on the rolling, we get or we can classify the carbon nanotubes in three types: armchair, zigzag, and chiral carbon nanotube. Now, in three methods, we have synthesized the carbon nanotube. Okay, which type of carbon nanotube will form? Whether armchair will form or zigzag will form or chiral will form. This formation we cannot control or we cannot decide the precipitation of carbon atoms. We can vaporize the carbon atoms. During the precipitation, we cannot control the precipitation as per our requirement. I want only armchair carbon nanotubes. It is not possible to synthesize 100% armchair carbon nanotube or zigzag. In similar manner, a chiral also. We may get the mixture of these things, either armchair or zigzag or chiral carbon nanotube. Let us see zigzag. What is this zigzag carbon nanotube? If you are rolling this carbon nanotube in this red spots, that is in this direction, that is in horizontal direction, if you are rolling your graphene, you get zigzag carbon nanotube. In this blue color line or blue color vector direction, if you are rolling, you get armchair carbon nanotube. The in between, that is in black color carbon atoms, if you are rolling, you get chiral carbon nanotube. See, armchair, see this armchair carbon nanotube, we are having armchair, just it is like a cyclohexane. You see that armchair form, exactly armchair. It is like a cyclohexane thing, just that's what we are naming it as armchair. Okay, since it is having armchair structure, this is armchair carbon nanotube. And second one is zigzag carbon nanotube. This zigzag, you see that zigzag manner carbon atoms are there. Zigzag, yes, zigzag manner carbon atoms are arranged. That's what it is, a zigzag carbon nanotube. Okay, armchair, zigzag. And in this case, you cannot predict whether it is armchair or zigzag. You see that it is asymmetric in nature. That means there is no symmetry. In this case, symmetry is there. In this case, symmetry is there. But in this case, it is asymmetric. That's what we are calling it as chiral. So we cannot, even if you are seeing the zigzag in this structure, but the orientation, that vector, whatever it is, it was like a slight tilting, just it was in a tilting manner. Okay, this is chiral carbon nanotube. Three types of carbon nanotubes: armchair carbon nanotube and zigzag carbon nanotube and chiral carbon nanotube. Carbon nanotubes and their properties. let us discuss four types of properties. One is electrical property, second mechanical, third vibrational, and fourth thermal. Okay, electrical properties, mechanical properties, vibrational properties, and thermal properties. One by one, let us. If you want to understand the carbon nanotube electrical properties, the electrical properties will be depending on the rolling vector. Okay. So what is rolling vector? Let us take single graphene layer. Okay, we have taken graphene layer and you give mn numbering like xy, how we are giving the numbering. Just let us give the numbering for carbon atoms. Alternatively, the carbon atoms which are lying on the same plane, just write 0 0, m is 0, n is 0, m is equal to 1, n is equal to 0, m is equal to 2, n is equal to 0, m is equal to 3, n is equal to 0, m is equal to 4, n is equal to 0, m is equal to 5, n is equal to 0. You see that in this direction, m is, in this direction, what happens? M is increasing. In this direction, m is increasing. The second, 1 0, after 1 0 again, 1 1, 2 1, 3 1, m is varying. We are increasing m number, but n is constant. That's what we are writing. N is equal to 0, n is equal to 1, n is equal to 3, n is equal to 4 for similarly up to n is equal to n. Okay. We have not numbered the entire graphene sheet. We have numbered only half of the graphene sheet because it will be if you are numbering all the carbon atoms, it will be very complicated. That's what half of the graphene sheet was numbered. Even if you want to reduce, still we can reduce this numbering also. Now mn based on the mn values, what we can write a vector that is c is equal to na plus mb. It's the n m or these values. Now based on this rolling vector, carbon nanotube will be exhibiting different electrical properties. That means either it may be conductive or it may be semiconductive properties. Now let us see how it will be getting metallic properties and how it will be getting semiconducting properties. Let us see mn both are equal in this red color. So here m is equal to n, here m is equal to n, m is equal to n, m is equal to n, m is equal to n. That means 1 1 2 2 3 3 4 4 5 5 6 6 7 7 8 8. In all the cases m is equal to n. In this vector, if you are folding the carbon skeleton, so what you get? You get armchair carbon nanotube. Armchair carbon nanotube. If you are folding in this direction, you will get zigzag carbon nanotube. In this case, red color spots are less. You see that if you are having 12 carbons, only 4 carbons, 5 carbons are having metallic properties. Remaining carbons, they don't have metallic properties. All these red color things are metallic properties. This white color, the semiconducting properties, the carbon atoms. Now, if you are rolling through this red color, you will get metallic. If you are rolling through this red and white, you get both. Either it may be semiconducting and it will be having this thing. And we are having a standard formula to decide whether zigzag is conducting or semiconducting. M minus n by 3. See that, let us apply for this red color. M is equal to 12, n is equal to 0. 12 minus 0 by 3. You get integer only. That means this red color is a metallic. And 11 minus 0 by 3, you are not getting any integer. That means this white color is not metallic. And this white color not metallic. This red color. 9 minus 0 by 3, you will get integer 3. And 8 0. If you are applying m minus n by 3, you will not. That means it is a real, it is not an integer. Now you get, if it is an integer, it will be metallic. If it is a not integer, what you get? You get semiconducting properties. Since in this direction, if you are folding the graphene sheet, you get either semiconducting or the metallic, both the things. But mostly Semiconducting thing, semiconducting nature will be more for zigzag carbon nanotubes. And for this armchair, it is conducting. It is a metallic carbon nanotube. They will be conducting electricity equivalent to metals. But in between these two, zigzag and armchair, through this, if it is chiral carbon nanotube, we get this chiral carbon 2m plus n. What is m and what is n? Just if you apply this, 2 9 18 plus 6 24, 24 by 3 you get 8 integer. Similarly 8 5 2 into 8 16, just you see 5 21, 21 by 3 7 metallic, 7 and 4 2 7 14 plus 4 18, 18 by 3 you will get 6 integer. You see that all these red color things will be divided by 3 and you get integer. Okay. Now this chiral carbon nanotube in this direction, if you are rolling, it will be metallic or it will be conducting. But if the same thing, this arrow, if it is coming through this white color carbons in this direction, if you are rolling, what will happen? This chiral carbon nanotube will be semiconducting. That means chiral will have two chances. Either it may become metallic, either it may become semiconducting. But zigzag semiconductor, chiral metallic or semiconductor, armchair only metallic. That means you see that based on the rolling vector, your carbon nanotube properties, electrical properties are varying. Okay. So now let us see what is this folding and how we can compare this. See that we can compare rolling. How we are rolling those just manually we are rolling this is, but carbon nanotubes we cannot roll it or we cannot fold it graphene sheet. Okay. We can control the electron movement, we cannot control the precipitation of carbon atoms. Let us take a simple example. Let us, if you are entering into the classroom, okay, I cannot control the sitting position of each student, where he is going to sit. In the similar manner, carbon atoms are precipitating while forming carbon nanotubes. So we cannot control the precipitation of carbon atom. That is what a main important parameter in this. Okay, we can, for understanding purpose, just I am showing this. You see that in this horizontal manner, if you are rolling, what you get? You get zigzag in this manner. If you are rolling in this manner, you get armchair. If you are rolling in this manner, in between, in any direction, in between, yes, in chiral, that means in between these three, in between these two, if you are folding the, that means this is the best example to understand the carbon nanotube electrical properties. Okay. Electrical properties of carbon nanotubes will be depending on the rolling vector of the carbon nanotube. If it is a horizontal one, it will be zigzag. If it is a vertical one, it will be armchair. If it is in between, that is chiral carbon nanotube. You can compare this thing with previous one. See, exactly it is looking like zigzag. Yes, zigzag, horizontal, and armchair vertical only. This is vertical only. Just you see this is in straight vector. That means it is in vertical. See, it is in vertical. It is in vertical, red color. It is in vertical. Okay. This is a chiral. Sometimes this chiral thing may be in between these two. That means 8.5 and 9.5. In between it will be. In that case, what it will be? It will be a chiral. Okay. Exactly. This is now this you cannot consider it as an chiral 100% because it is equivalent to parallel to armchair. It is a armchair only, but in between these 2 points, if you are keeping, that is a chiral. or anywhere in between these two things. If it is coming chiral, anywhere in this between two, if you are folding or if it carbon nanotube is rolling in that vector, it will be chiral. Electrical properties of carbon nanotube will be depending on the rolling vector. We know how we are rolling and what will be the position of carbon atoms and what is its nature based on these formulas. Okay. Now zigzag m by m minus n by 3, if it is integer, it will be having metallic properties. Armchair, this is m is equal to n. It is a metallic, 100% metallic, and chiral in between. If suppose if 2m plus n by 3 equal to integer, metallic properties dominates. If it is not, semiconducting properties will dominate. That means either it is having a chances for both. Okay, it depends on the rolling vector of the carbon nanotube. Based on the total these three rolling vectors, your carbon nanotube will be having or it will be exhibiting different electrical properties. Now, if suppose if it is semiconducting or metallic, how the band gap of those carbon atoms or each carbon atom or the entire graphene sheet or entire carbon nanotube, how it will be, it will look like this. For semiconducting, we can see clearly the gap here. You see that for metallic things, if it is there, both VB and CB will combine. Okay, it is a simulated diagram. Just see that there is a small gap between VB and CB. This is a semiconducting thing. For metallic things, definitely there won't be any gap. These two things will be merged. These two things will be merged. There won't be any gap between VB and CB. These are the 6 carbon atoms. You see that? Yes. All 6 carbon atoms only we are seeing. Each carbon atom thing by simulation, by we are getting this type of band gap structure for single hexagon. This is for single hexagon. Similarly, it will be for all carbon atoms. In order to understand the band gap of the graphene or carbon nanotube, just we are taking this diagram as a reference. Now, carbon nanotubes and its mechanical properties. Carbon nanotubes mechanical properties. Carbon nanotubes tensile strength is high, Young's modulus is high, thermal conductivity will be high, density will be less. See the strength of carbon nanotubes. Carbon nanotubes are very strong and the tensile strength of CNTs is 100 times stronger than steel. You see that what we feel steel is the strongest material, but though the tensile strength of the carbon nanotube is 100 times higher than steel. See the strength. That means carbon-carbon covalent bond is a very strong bond. Though it is an covalent, but covalent bond is the strongest one. We can take a best example, even diamond. sp3 covalent bond, it is a very hard. Similarly, graphene, though it is having sp2, but why this tensile strength of these carbon nanotubes and this graphene, it is very high because all carbon atoms, let us see in these carbon atoms, they are having covalent bond. So now there is no dislocation. That means every carbon atom is occupied by carbon, the position. So now what happens? There is no dislocation in this sheet. That means it is very strong. If any dislocation is there, it is not strong. That means covalent carbon-carbon bond is very strong. That's what carbon nanotubes are very strong, and even tensile strength is 100 times stronger than the steel. And because of even interlocking of carbon-carbon bond was locked, like an it cannot rotate or anywhere, or it's like an cyclic thing. 1,3-butadiene, if you are, is a bond, a cis and trans can be 1,3-butadiene. Okay, it will be having two forms, cis form and trans form. Here it was locked, interlocking of carbon-carbon covalent bond. Due to the locking of this carbon-carbon covalent bond, the graphene layer or carbon nanotubes are very, very strong. Okay. It doesn't have any grain boundaries or dislocations. That is, it is tensile strength is very high, and Young's modulus of single wall and zigzag, chiral and armchair, what it will be. You see that the Kevlar bulletproof material or stainless steel is what is the Young's modulus, the in terapascals, and single wall nanotube and armchair and zigzag. You see the ratio between these two values, the ratio between these two values, you see this 1 to 5, approximately 1 terapascal single wall carbon nanotube, this Young's modulus, and the tensile strength 13 to 50, and tensile strength of stainless steel is 0.3, and Kevlar is an organic material, and the tensile strength and Young's modulus of this material is, you see, so mostly this Kevlar material they will use in bulletproof jackets. Okay, and even if you compare with bulletproof jacket, just you see the strength and Young's modulus of the carbon nanotube and elongation of the carbon nanotubes. Even carbon nanotubes will have elongation property and elongation break percentage, you see, for the stainless steel and carbon nanotubes. It is quite comparable. But if you come to the tensile strength and Young's modulus, the values of the carbon nanotubes are very high. Next, thermal conductivity. Why carbon nanotubes are thermal conductors? Due to the carbon-carbon covalent bond, and due to this interlocking, they will be getting good mechanical properties. Mechanical properties of carbon nanotube can be explained by carbon-carbon interlocking. Okay. Now, if you come to the thermal conductivity, how will you explain the thermal behavior or thermal conductivity of carbon nanotube? Just the heat will be transferred through carbon-carbon covalent bond through the vibration. Why this thermal conductivity of the carbon nanotubes is high? Due to the transfer of heat from one carbon to another carbon by vibration. That means this, even we can consider it as a vibrational property. Okay, thermal conductivity will be happening through the carbon-carbon vibration. Due to this vibration, what will happen? Heat will be transferred from one carbon to another carbon. Let us see in this diagram. If thermal conductivity, let us heat we are supplying at this point, what happens? The heat will be transferred from carbon to carbon through vibration. That means this carbon-carbon is it will vibrate, and through vibration the heat will be transferred. Similarly, this carbon to this carbon, like an electron movement, like an electron delocalization. Similar manner, the heat will be transferred from one carbon to another carbon, and the thermal conductivity of the entire graphene sheet or carbon nanotube will be high. This is the explanation for thermal conductivity of CNT. We have discussed three properties. Electrical properties will be depending on rolling vector, and mechanical properties will be depending on carbon-carbon interlocking, and the thermal conductivity of the carbon nanotube will be depending on carbon-carbon covalent bond and through vibration. So now, if you come to the application part of carbon nanotubes and polyrenes, graphene, all are made up of with carbon atoms, and we don't have any hydrophilic atom or hydrophilicity generating things on carbon nanotube. So now the biggest challenge is, if you want to disperse carbon nanotube in water, it is very difficult. Now what we have to functionalize the carbon nanotube with either acidic or basic things, either from sulfonic groups or carboxylic groups or amine groups. We have to introduce on carbon nanotube surface by, not by physical mode or by electrostatic interaction. We have to functionalize it with covalent manner. Covalent manner means what? You see this, chemically it is forming a bond on carbon-carbon nanotube, and this is called covalent functionalization. Electrostatic means due to the charge, or due to the hydrophilic or hydrophobic, due to hydrophobic interaction. Just if you are doing any functionalization, that is a non-covalent functionalization. That means in order to improve the solubility of carbon nanotube, we are going for covalent functionalization or non-covalent functionalization. This is what the way to improve the dispersion ability of carbon nanotube in water. Okay, this is one of the important step or parameter for carbon nanotube. Carbon nanotubes are made up of with carbon atoms, and water is an oxygen and hydrogen. Just you see that this is an hydrophilicity, and that is an having an hydrophobicity. Now how will you disperse this hydrophobic material into the hydrophilic water? We have to do the functionalization by covalent manner or non-covalent manner. Means it will be forming a new bond, covalent bond. Here it won't form a bond, but due to the charge or any other electrostatic interaction, we are functionalizing the carbon nanotubes. And carbon nanotube properties comparison: electrical, mechanical, and thermal. This is in simple table. You can see thermal conductivity of carbon nanotubes and the copper. See here, if you compare, so what it will be. Now we will discuss the applications of carbon nanotubes or carbon nanomaterials. Carbon nanotubes can be used as electrodes. You can use it as a catalyst. We can use it as an actuator or transistor, membranes, a capacitor, and sensors. See, carbon nanotubes will be used as an AFM tip, atomic force microscopy. We'll be having a pot called cantilever. Okay, in cantilever, just they will grow the carbon nanotubes on cantilever surface, and this is the cantilever, and this is the cantilever. This is the AFM tip, atomic force microscopy. They will be using cantilevers. On the cantilevers, mostly the carbon nanotubes can be used as a tip, AFM tip. Carbon nanotubes, actuators. See that if you are supplying electrical energy on these materials, what it will be? It will be generating a mechanical force. It is exactly opposite to dynamo. What is dynamo? This is mechanical energy will be converting into electrical energy. That is called dynamo. Exactly opposite to the dynamo. If you are supplying electrical energy, it will create mechanical motion in the material. That means carbon nanotubes even can be used as an actuators, That means carbon nanotubes based actuators can be developed. And carbon nanotubes can be used in touch screens due to the electrical property, due to the thermal property. So we can use in touch screens. And carbon nanotubes can be used as a drug delivery agents. And drug delivery, before going to drug delivery, what we do, just we will functionalize the carbon nanotube. After functionalization, just you see here in the at present slide, carbon nanotubes are functionalized with liposome conjugate base. Okay, and this material can be delivered inside the cell wall, because of this hydrophobic thing, and our cell wall will be having hydrophobic nature. Due to that, it can enter into the cell wall and it can deliver the drug in particular or in specific place. Carbon nanotubes, artificial muscles, artificial eye, artificial fingers can be developed with the help of carbon nanotubes. And what is the advantage of these artificial objects? Artificial nose can be, artificial eye can be. The advantage of this artificial eye or nose, we can quantify the parameter. That means smell, we can quantify. But with our nose, a physical, it's a human nose, what we can qualitatively tell, we they sense the gas smell and we cannot quantify it. But the artificial muscles or artificial these artificial carbon nanotube based artificial fingers or eyes or nose, we with quantification we can do the things. Similarly, as a catalyst, we can use the carbon nanotube composites for degradation of dyes in textile industry, and the carbon nanotubes will be used for hydrogen storage. Even both graphene and carbon nanotubes, it is like a composite. Both are nano. These pillars are like carbon nanotubes, and this plane is like a graphene. See that. This Rice University, even recently they have reported, and they have developed the experimentally they have developed the graphene and carbon nanotube based material for hydrogen storage, energy storage material. Even lightning is one of the important problem in society. Just see that due to the lightning, what will happen is a natural it is like a natural disaster. In order to, even sometimes the plane crash will be, in order to avoid these things, what we can coat our aerospace or equipments with graphene or carbon nanotube materials or carbon nanotube composite materials, and we can avoid these things. And even flexible electronic devices, we can MEMS development, sensors, even for chemical sensors. Sensor may be anything which is detecting minute physical or chemical change. So EMI shielding materials and flexible electronics, sports equipments, and aircraft components. These are the applications of carbon nanotubes. Thank you for your patience. So now session is open for discussion. Yes, please ask me the questions. If you are having any doubts in this, please let me know. You can unmute yourself now and please ask me the questions. If you are having any doubts. So what is the time now? Around. So functionalization is nothing but covalently we are anchoring in order to improve the hydrophilicity. Carbon nanotubes are hydrophobic. Okay. So now if I am treating the carbon nanotube with sulfuric acid, what will happen? These sulfonic groups will be sitting on carbon nanotubes. Now, due to the sulfonic groups, what will happen? Carbon nanotubes will get hydrophilic. So now what I can functionalize carbon nanotubes, I can disperse in water. If you want to use it for medical or biomedical applications, solubility is one of the important thing. That's what these most of the tablets solubility, they are partially soluble in water. So whatever milligrams, maybe 100 milligrams or 500 milligrams, entire milligrams will not soluble in our body, because the solubility, they might be having solubility problem. Maybe 10 milligram or 20 milligram is soluble, and only the 10 milligram and 20 milligram only will be acting on our disease or whatever it is. Okay. Similar manner, carbon nanotube we are functionalizing. Functionalization can be done covalent by formation of bond, or otherwise by electrostatic interaction. Let us, carbon is having hydrophobic, and maybe you can keep an hydrophobic thing another side and hydrophilic another side. Due to hydrophobic, what will, it will attract, and outside it will be hydrophilic. Like that, non-covalent functionalization can be done. Yes. Yes, please let me know if you are having any doubts. So for CAE 2, Unit 3 and Unit 4, fullerenes and carbon nanotubes will be there. Synthesis of carbon nanotubes and applications, and fullerenes synthesis. So mostly these properties I will let me discuss, maybe if possible by tomorrow also. We have to finish only the LCD. Okay, this half an hour is enough to finish the LCD. So with that, this third and fourth will be over almost 90-95%. The two class, hardly 1 hour or 2 hours is enough for us. Okay. Third chapter will be there, and in fourth chapter, fullerenes and carbon nanotubes. Synthesis of carbon nanotubes by CVD method, chemical vapor deposition method. I have already forwarded the material to you. Okay. If you are having any doubts, please let me know. We will discuss even once again if possible. Yes, somebody. Now have you understand the functionalization? The material, whatever I have forwarded to you in group, that is enough. You prepare that first. Unit 3, 4 questions. That is conduction mechanism in polyacetylene and polyaniline, organic solar cell, organic light emitting diode, and LCD. The 4 questions. That's it.
Sir, once again, can you repeat it, sir?
Which one?
Long answers for third lesson, sir.
Third lesson. Okay, tomorrow shall we?
Okay, sir.
Tomorrow we'll take LCD, and after that we will be having maybe 10 or 20 minutes. That time we will repeat. Okay, we'll revise
Okay.
once. Okay, unit 3
Okay.
revise. Yes, whatever we have, that is enough. You prepare according to the unit 3. I have already forwarded. Okay. Yes, shall we stop? Shall we wind up the class?
Yes, sir. Thank you, sir.
Yes.
Thank you, sir.
Okay,
Thank you,
110. Okay, we'll close it.
Yes, sir.
Okay, thank you for your patience. Okay.
Thank you, sir.
Okay.
sir.
Yes, Rahul, you take my number and just you send a message. So is that? Okay. I will add it. Unit 4 only we are having 3 questions. One is fullerene, one is carbon nanotube, and another one is graphene. Maybe this carbon nanotube is having 2 questions. One is electrical properties. The diagram we have discussed, no? That diagram we have to give an explanation. That is electrical properties. Synthesis is 1 question and electrical properties 1 question. Totally we have finished 3 questions. Only the remaining thing is graphene synthesis and applications we see. Okay, shall we close?
Yes, sir.
Yes, sir.
Thank you.